Hello. In this tutorial, we will create a Van der Waals equation by expanding a damping oscillator model. To begin with a damping oscillator model, let's download the model from physio.jp. Click an icon of a folder with a globe mark. A dialog opens and select damping oscillation with dBID equals 800 in the dialog. Then click Download button. You can select the way to open the model on the canvas. Now click Open button in the small dialog. If you already have a model on the canvas, and you want to add a new model to it, then select Add here. Now you see the damping oscillator module on the canvas. Before starting to edit the model, I will explain how we modify the model to create a Van der Waals model. The equations of the damping oscillation are shown at the upper right-hand side of the slide. In the damping oscillator, the parameter k was a constant value, but now we change it as a function of x, that is k is x to the second power minus 1. Hence the Van der Waals model is an oscillator with a nonlinear damping term. Notice that when the absolute value of x is larger than 1, the value of k becomes positive. Hence the oscillation is damped, and when the absolute value of x is smaller than 1, then k is negative, meaning the oscillation amplitude enlarges. We'll use x equals 3, v equals 3, as the initial values of the variables x and v. Okay, now we will modify the physical quantities defined in the module. Select Edit Physical Quantity in the context menu. Then select the entry of the parameter k in the table. At first change its type. Now it is static parameter, but after this modification, the value of k will change in time according to the value of x, so now it should be a variable parameter type. Then go to Implementation tab to modify its definition. K is x to the second power minus 1. Exponential notation can be written with a function POW. And click OK to finish. Don't forget to change the initial values. Of course it is possible to change them on the dialog, but there is another way. You can change the values directory on the table at the bottom of the main window. Double-click on a cell, then the cell becomes editable. Now the values are 3 for both of v and x. Let's change the name of the module to Van der Waals, and also change the name of the model accordingly. Save the model with different name. Alright, now let's run a simulation to check the dynamics. Select Flint from Simulation in the menu bar. Flint is launched with the model. Click Run button to execute a simulation, and go to Detail and View to observe the graph. At first, let's observe the dynamics of variable x. Move the variable x from the leftmost list box to the y1 box. The graph of x is shown in the center panel. It stably oscillates. Now let's observe the dynamics on a phase plane spanned by x and v. Move the variable x to the abscissa box, and drop v to y1 box, and remove time from y1 box. The orbit starting from x equals 3, y equals 3, twists around a periodic solution. The periodic solution is a stable limit cycle. Let's change the initial point to observe how the orbit looks like at the different initial condition. Go to Parameters tab at the main window of Flint, and change the initial values to 1 and minus 3, and click Run button again. This time again the orbit twists around the stable limit cycle. Finally let's try the third initial point, which is 1 and 0.5. This initial point is inside of the limit cycle. Again the orbit twines up to the limit cycle from inside. We can analyze the properties of the vector field with a little bit mathematical way. Direction of a state point's movement on a phase plane can be estimated by the relative location of the state point to null lines. The null lines are solution of the equations that derivatives of dynamical variables with respect to time are 0. In this case, The solution of dx dt equals 0 is v equals 0. Hence the line v equals 0 is called x null line. The solution of dv dt equals 0 is v equals x over 1 minus x square, which is y null line. For example, on the x null line, dx dt equals 0, which means there is no movement along x-axis. Hence the state point must cross the x null line vertically. Similarly, the state point crosses y null line always horizontally. These two conditions already gives you some idea about the dynamics on the phase plane. Besides, in the area between the x and y null lines, you can roughly guess the direction. It should be simply between horizontal and vertical. The signs of derivatives of x and y are also important information to estimate the direction. In this case, the orbit starts from left upper part of the phase plane. At first, it goes to the lower right. It crosses the y null line horizontally and reverses the direction along the y-axis, because after crossing the y null line, the sign of the derivative of y reverses. In this way, at the second crossing on the y null line, the state point moves to the lower right. Then after crossing the x null line, the direction of the state point reverses horizontally and returns to the upper left after crossing the y null line again. And finally you see a stable limit cycle. A stable limit cycle has an interesting property. If there is only one stable limit cycle in the phase space, all orbits twine up to the limit cycle. So, for example, assume that a state point moving on the limit cycle suddenly receives some perturbation, and the point deviates. But after a while, the state point goes back onto the limit cycle. This is one of underlying mechanisms of a robust oscillatory behavior. Alright, this is the end of this tutorial. You can play more with Van der Pol equation on Flint, with different parameter values and initial values. See you next time.